Hello everyone, welcome to the 29th episode of this series. In this video, we learn how to compute rank and dimension without using row reduction. So far, we have seen algorithms for finding bases and dimension of special types of subspaces. This is the note where we ended our previous episode. In this episode, we want to compute rank and dimension without using row operations or row reduction, but do note that this can only work to a certain limit and only in certain cases. Okay, so we saw last time that for a fixed matrix A, we have two simple formulas. We have that the dimension of the image space of A is always the rank of A, and the dimension of the kernel space of A is the width of A minus the rank of A. Note that both of these formulas require the rank of A, which typically requires row operations, but the sum of the two formulas does not require the rank. And this brings us to a very important theorem in this course, the rank nullity theorem. So if A is a matrix, any size, then the dimension of the image of A and the dimension of the kernel of A always add up to give us the width of A. So you essentially take the two equations and you add them up and you get that the sum of these two dimensions is the width of A. So the dimension of the image of A is called the rank of A, of course. And the dimension of the kernel of A is called the nullity of A, and that's just another word for it. So let's start with an exercise. So we're given a 3x3 matrix A, and we're given a crucial piece of information that the image of this matrix is a plane in R3. So the collection of all the image vectors of this matrix forms a plane in R3, and we have to find the dimension of the kernel of A. So we saw an explicit algorithm to find a basis and therefore the dimension of the kernel of a matrix A in the last episode, but that required row operations or row reduction. And in this problem, we want to avoid that, and we just want to use the rank nullity theorem or related facts to compute this dimension. So because the image of A, the plane in R3, we get that the dimension of the image space of A is 2. Now, because the width is 3 for this matrix, there are 3 vectors, therefore, or 3 column vectors, therefore the width is 3. The rank nullity theorem gives us that the dimension of the kernel is the width of A minus the dimension of the image space of A, and that is just 3 minus 2, which is just 1. So geometrically, what this means is that the set of vectors that are mapped to 0 by the linear transformation corresponding to A is a line passing through the origin. And it's a line because the dimension of that object is 1. So, one is going to ask, like, what dimensions are possible and like, what do they really tell us? So let's look at some special cases. So the first is the zero subspace. So the zero subspace of Rn is the subspace that only contains the zero vector. And we've actually seen this in some of our problems at this point. And note that this is the only subspace with finitely many elements. So if you have a subspace which has any other element other than the zero vector, then by closure of scalar multiplication, you're going to have infinitely many elements. The next thing is the subspace of dimension 0. So this zero subspace is the only subspace of Rn for any n with dimension 0. And the last thing is matrices of rank 0. So the only m cross n matrix of rank 0 is the 0 matrix, because anytime you have a non-zero entry in any matrix, you're going to have at least one leading one in the row echelon form. So the rank is going to be at least 1. So to get a matrix of rank 0, you need to make sure all entries are indeed 0. So we can also consider the case of maximum dimension, and by maximum I mean maximum inside an Rn. So if we have like Rn, then any subspace of Rn can have a dimension at most n. But if it does have dimension n, like a subspace of Rn, then it is actually going to be Rn itself. And that's what I have for the next fact. And for matrices, this concept of maximal rank isn't unique. In other words, any invertible matrix has the largest possible rank. So the last special case I want to look at is the case of subspaces with dimension 1, because when you have a subspace that is one-dimensional, all of its vectors are going to be multiples of each other. And the same goes for a matrix of rank 1. So if you have a non-zero matrix which has a rank 1, then all of its columns are going to be multiples of each other, and vice versa. So if you have a matrix with all columns that are multiples of each other, its rank is going to be 1. So for example, in this 3 by 3 matrix, my columns are 1, 3, minus 1, 2, 6, minus 2, and minus 1, minus 3, 1. Clearly, 2, 6, minus 2 is 2 times the first column vector, and minus 1, minus 3, 1 is minus 1 times the first vector. So all the 3 column vectors are multiples of each other, and therefore its rank is 1. And you can actually compute that, and it's going to be the case. Okay, so let's look at an exercise. So we're given a 2 by 2 matrix, and we want to find the rank of this matrix and then the dimension of the kernel as well. So because A is not the zero matrix, because there are non-zero entries in there, its rank cannot be 0. And because the columns are not multiples of each other, its rank cannot be 1, right? Because 2, 1 is not a multiple of 1, 2, or vice versa. So, the rank cannot be equal to 1. Now, because this is, a 2 by 2 matrix, the rank can be at a maximum 2. And since it's not 0 or 1, it has to be 2. Now, because the width of this matrix is 2 as well, we get that the dimension of the kernel, which is given by width minus the rank in the earlier part of this episode, is just 2 minus 2, which is 0. Okay, so let's look at another exercise. This time we have a 3 by 3 matrix, and we want to find its rank, the dimension of its image space, and the dimension of its kernel. So similar to the last problem, because B is not the zero matrix, its rank cannot be 0. Because the third column is not a multiple of the second or the first column. We have that not all columns are multiples of each other, so the rank cannot be 1. But do note that the first and the second column are multiple of each other, and we get that determinant of this matrix is going to be 0, and that would imply that this matrix is not invertible. And if it's not invertible, it cannot have rank 3. So what we've shown so far is that this matrix, which is 3 by 3 in size, cannot have rank 0, 1, or 3. So the rank of this matrix has to be 2, which is the same as the dimension of the image space of B. So we get 2 answers for the price of 1. And because this is a 3 by 3 matrix, its width is 3. And therefore, we get that the dimension of the kernel is the difference of the width and the rank of B, which is 3 minus 2, and therefore 1. Now, before ending this episode, I just want to mention 2 results. The first relates dimension to containment between subspaces. So what I mean by that is the following. So if V and W are subspaces of Rn, and we know that V is a subset of W, so V is contained in W, then the dimension of V is going to be less than or equal to the dimension of W. But if V is contained in W and we also know that their dimensions are the same, then V is actually equal to W, like as subsets or as subspaces of Rn. So what this actually means is that if I have two subspaces V and W, and V is contained in W, um, and if this containment is proper, that means there are actually elements in W that are not in V, then the dimension of V will be strictly smaller than the dimension of W. But if they're actually the same, then they're going to have the same dimension as well. The other fact relates rank and matrix multiplication. So it just says that if you know the rank of any two matrices, um, then you can say something about the rank of the product of the two matrices. So in particular, the rank of AB is going to be less than or equal to the minimum of the rank of A and the rank of B. And with this, I would like to end this episode. Hopefully things made sense. I do want to add that we're actually going to prove this last fact in class as an exercise. So I will see you guys soon. And up until then, happy learning.